Okay, let's start. Good morning. Uh, so today we'll talk about Romberg integration. And for that, I will remind you of Simpson method. After that, the trapezoidal method, and then notice something and find that we can make it seems we can make the trapezoidal recursive way or method more accurate only with playing only by playing with the numbers that we already got. Okay. So the simple method say that we take a function in each segment from x0 to x2, from x2 to x4. And in each segment, we take a quadratic function that interpolates the function in the 3 points at that segment. The 3 points are x0, x0 plus h, and x0 plus 2h. And here, this is the function itself, and the interpolation is a parabola here, parabola here, parabola here. Okay. And you know how we do this polynomial interpolation using Lagrange polynomials or Lagrange method for interpolation. And then we perform the integral. Okay. And the answer of the integral is like this. We take third of the first value, 4/3 of the second value, and third of the third value, which is at x2, multiply by h, and then we get an error of h to the fifth. After that, we compose this the range of integration a b till 2h multiplied by some natural number n, and each segment of these we calculate it like this. And I said here O of order h to the fifth. The real number that I can use is -1/90. We can prove that multiplied by the fourth derivative of the function at some point psi j, where psi j is a point between what and what? Yes. Psi j is between x2j minus 2 and x2j. And when we add n/2 of these numbers, we get I think here we should n/2. Okay, depends what we call n. Okay, so it's h to the fifth divided by 90 or 180. It depends what we call n. And now one of these h's go to b minus a, divided by n or n/2 or 2n. Therefore, the error is of order is. And an example of this, because we know that it's h to the fourth, that means that if we divide the segment to 4, if we divide the range to 4 segments, we get 1/4 to the fourth from our previous error if we take one segment. So that's it. If we take it as one segment, which means h equals what here? So what one segment of 2 h's. So h here equals 1, and h here equals here, a quarter, yes. So we expect that the error is somehow 1 over 4 to the 4th or quarter to the 4th, and it really is. That's the error when we calculate with h equals 1, and that's the error when we calculate with h equals 12. So that's the Simpson rule. And I want you to remember that it's with an error for a composite way of integration, the error is h to the 3rd. It goes like it. Now, I will call this Newton-Cotes method. It's called like that. You didn't mention this name, whether or not, but that's the name. Now we can take A to B. That's B, that's A, and divide it to, let's say, n segments, but at each segment, we take m plus 1 points. And we interpolate the function using, at this segment, using these points. So if we have here x0, we have here xm, and here x2m, where xm minus x0 is mh, and b minus a is n m h. Okay. So you know the Riemannian method was with m equals 0. Yes. And the trapezoidal method was with m equals 1. And that Simpson method, yes, this Simpson method was with m equals what? 2. Okay. So it's straightforward. We interpolate the function here, and here I'm writing this only for you to see, maybe at the first time, how we can talk about the error in some rigorous way. Okay, so here I will somehow try to find the error, the exact error. I will try to find the minus 1 over 90 for you to see that, but I will not succeed. Okay. Okay. So you know this is the polynomial that equals 1 at xj and equals 0 at every xi which is not xj, and the interpolated function, I call it f hat, is the sum of the product of yj lj of x, and then we integrate. That's how we try to approximate our integral. So we interpolate the function here, integrate. We interpolate the function here, integrate. Here and integrate. And I'm talking now about only this first segment. So I hat is the integral over f hat, and I integrate over each polynomial of these. That's the weight of the evaluation of the function at some xj, and then I get the sum. Okay. So the wj's are the integrals over the LJ's, or the areas under these functions. And now I will try to estimate the error. How can I estimate the error? I will say that I know what is the error here. Okay, I know how I know some form of the error of f of x minus f hat of x. So for that, I will use what you know from calculus. I will build a function that has n plus 2 zeros at this one. So how can I build this function? I know that my interpolation equals the original function here and here and here and here and here. So here and here and here and here. Okay. So these are n plus 1 point, n plus 1 point. I want another point that the function is 0 at. So I build the function f minus f hat of x minus some constant at some point xp. Okay. Here I choose some point xp. Let it be here. Okay. So my final goal is to write down a form of the error of the function of my evaluation f hat at xp. Okay. So if I want the error at xp, I take this form f minus f hat. You can call the function f xp of x. That's it. So f minus f hat, it is 0 at each point of x0, x1, x2 until xm. And this function is also 0 at this point. And I choose the constant c so that this is 0 at xp. How can I do that? Like this. Okay, so that's the CP, the C of xp. Now we assume, of course, that our original function, let's say it's has up to the k plus 2 derivatives continuously, and because of that, we know now that this function fxp of x at this segment in x0 up to x2m has k plus 2 zeros or roots. Therefore, by Rolle's theorem, its derivative has k plus 1 or m plus 1, I'm sorry, m plus 1 zeros. And again, by Rolle's theorem, the second derivative of it has m zeros. Okay. And we do this inductively. And then finally, the m plus 1 derivative of f has at least 1 0 at this range. Okay. This 0, I don't know at which point, but I call it xi. It is some point between x0 and xm. Okay. And I know now that f at xi, there is some xi that the m plus 1 derivative of f is 0 at. Okay. Now, what's the k plus 1 derivative of this function? It is the k plus 1 derivative of this minus Cp multiplied by what? By m plus 1 factorial. Okay, that's the k plus 1 derivative of this. The m plus 1, I'm sorry. And the m plus 1 derivative of this is what? 0, because this is a polynomial of order m. Okay. So at this point xi, I have this. Because f equals 0. F, the m plus 1 derivative of f. And this c that I know it it is this, equals f n plus 1 at psi divided by n plus 1. So, therefore, I know now that f minus f hat equals this. Okay? And I did this for any point xt. Okay. Of course, at the points themselves, the error is 0, because we interpolated the function there. But at any xt, which is not one of these points, but it's an intermediate point, that's my way of writing down the error of my interpolation or estimation or approximation. Okay.
Why does this have m plus 0? Because we have m plus 1 polynomial to the right.
Because it is 0 at each point of these, and it is 0 at xt. Yes. By construction, I defined it to be 0 at xt. Okay, so that's for you, maybe for the first time. That's the error of our interpolation or Lagrange interpolation. Okay, and now we will integrate over this. Okay, so how can I estimate my error? Okay, so the error of the integration is I minus I hat, which is this, which is the integral over this. And we can prove that this function, psi of x, is continuous, but it is psi of x. It's not some psi. At each xp, I have another psi. So at each x, I have another psi. So it's psi of x, and we can prove that it's continuous. And we somehow want to use, it is only a change of variables, so it's not important, but it's important. Now we want to use the mean value theorem for integrals. But the mean value theorem for integrals says that only if this function is continuous and this function doesn't change sign in the range of integration, only if this is true, I can say that this is a function of x, okay? This is, we can call this g of x. I can say that this integral equals to g of zeta, where zeta is some point between x0 and the integral over this, okay? But this is only when this doesn't change sign, but it changes. It changes sign because when we go from x0 to x1 and x1 to x2, this changes sign. Okay. So here's an example. See, x1, x2, x3, x4. So if x is here, so x minus x0 is positive, and all of them are negative. Okay. So it's a multiplication between them. But when x is here, this is not. Okay. So I can do something. Not that I cannot. I can do something. I can say that, okay, this integral is the integral from x0 to x1 plus the integral from x1 to x2 plus up to the integral from x minus 1 to xn. And then calculate this and then say, here I have this function multiplied by this function, and this integral equals to some point of f, let's say zeta 1, or zeta 0, let's call it m plus 1 factorial, the integral over this multiplication plus similar thing but with zeta 1, okay? And this integral will not be the same, okay? This maybe will be positive, and this is negative, and this is positive, and this is negative, and then I can bound the error, okay? I can bound the error. The error goes like what, you think? The error goes like h to the m plus 2. Okay, because we have here m multiplications, and we have here h squared. Yes.
Zeta depends on x, no? So some constant. You can't put it out.
It is zeta of psi of x, which I call it zeta.
But it's constant in some segment,
Of course,
but it depends on.
it depends on h. It depends on h. It doesn't depend on a x. X is an integration.
Yes, so how can you put it out of integral?
Huh?
I don't understand why you put it out of integral.
Okay. Okay. The mean value theorem says f has more and more. It says that if we have f of x multiplied by g of x dx from alpha to beta, this equals, if this is continuous and this Riemann integrable and doesn't change sign, this equals to f of psi at some psi. That's how we write it. As alpha beta, such that f of psi, the integral alpha to beta of g of x dx. Okay. Okay. So now we have, let's call this h. Okay. H. So now we have h of x equals a f plus 1 of psi of x. Okay. And g of x is that multiplication. Okay.
No, I said I didn't know there was such a theorem. I said I didn't know there was such a theorem.
Ah. Okay. You didn't prove it in calculus? No?
Not going to go. Not going to go.
Oh, okay.
Calculus one.
But you proved at least that that the integration of f of x dx over b minus a is f of c for some c. Yeah.
Well, we've only taken calculus one, not two. Calculus one is the series.
Okay, so this is the limit of the series.
Not the
Not
calculus
the-
series. This is a calculus two. We didn't take.
Okay. No, I mean this is the This is the limit of averaging the function, which is the intermediate theorem, intermediate value theorem. Okay. So I can find some bound for this. And if I calculate it, for example, for m equals 1, I can find, for example, I don't remember, but I can find that it's bounded because now I find bounds for these and I I take the absolute value of this and the absolute value of this, and I can bound them. Okay. For example, I can find that it goes like h to the fifth over 6 or over 12. I don't remember. But it is not good enough, and we can prove somehow this statement. Okay. We can prove this statement. For m equals 2, I meant for m equals 2. So how can we prove this statement? Okay, the way is to say this problem that the function changes sign, I will overcome it by making some polynomial that its error doesn't change. So I make another polynomial, which is not a polynomial of order 2. It will be a cubic polynomial, and I demand another condition. So I ask the interpolated function to be equal to the function here and here and here, and I add another condition which is about the derivative of the function at this point, and it will be a cubic polynomial, and this cubic polynomial will have somehow we can take care of it such that it has an error that doesn't change, that it's g of x, this multiplication doesn't change sign, because it will have x minus x0 and x minus x1 squared and x minus x2. Okay. Somehow, so this square will take care of that. And then calculate the integral over the interpolation function, and then find the error. And the answer of that integral of the interpolation function will be the same as the answer of the quadratic form. Okay, so we build, and so we have this quadratic function of interpolation, and we say that I equals the integral, and we build another interpolation function, and this integral will be equal to this. With some magic or miracle, it is not, okay? But that's how we do this. So it is not so easy to get this number, but it's true, okay? Any questions? Okay, but at least we know that for the trapezoidal, for m equals 0, for m equals 1, I'm sorry. For m equals 1, the trapezoidal 1, I know that the function doesn't change sign. Okay? So at least let's do it for it. So the integration is from x0. So anyway, for m equals 1, we can calculate this and say that for some psi, this is true. Okay, so this is the minus h cubed over 12 multiplied by the second derivative. Okay. So now you cannot say that in the course you neglected the errors completely. You know now at least how to find them, or how to search them in Google. And again, you will find many proofs that tell you this is minus h to the fifth over 90, but they are not two. Okay, the proof is what I said now. You have to build a cubic interpolation. Okay. Now let's remember what's the trapezoidal method when we compose it. So forget about n+1 points. It's only 2 points at each segment. And the trapezoidal method is to take h over 2, that's h. So that's the function. So we take this, and we take this trapezoid, and we take this. Okay, so it's h over 2, f of xi plus f of xi plus 1, and we sum from 0 to n minus 1. Okay. And the error is, as we said, it is minus h cubed over 12. And when we add many segments of this, so we have f double prime at xi, where xi is between yes, it's between xi and xi plus 1. And one h here is b minus a over n, and this is the average of the function, and there is some point, let's call it zeta also, or xi, which this average equals to the function evaluated at. Okay. Therefore, we say that the composite trapezoidal rule has an error of order h squared or of order 1 over n squared. Now, if n is very big or very large, this equals to what? Approximately. That's the something that you have to notice in order to find the new method. Think about the new method. If n is large, what does this equal? Approximately. Yes, it is. It is the average of this function at the range from x0 to xn. Or yes, to be from A to B. Okay. Why? Because if we have some function, we divide this, we say, let's take the average of these values. And after that, the average of these values, all of them. And n gets larger and larger. So it's the average of the function. Okay. And it's the Riemann integral. It's the Riemann integral divided by b minus c. Okay. So this 1 over n is 1 over b minus a over the sum of xi, let's call f double prime b. So that sum xi I, but the xi I get too close and too close. In the okay, so you have to to prove that, but in the Riemann integral, you said that if this psi I is x0 plus IH, this is H, and the H goes to 0, this is the integral. Okay, that's the Riemann integral. So there is another way of defining the integral. It's one. Right, I think you can divide the AB range to many segments where each one of them goes to 0. In some way, you have to define that. And this is also the integral. This will be also the integral. This way of definition is called the Darboux integral. Darboux. And we can talk about the supramodes and inframodes. Anyway, I think that you agree with me, and you see that at least that if we take very large n, very large n, so every psi I will be between the xi and xi plus 1. It doesn't matter if this point is here or here. Okay? If n is very large, this will be approximately the average of the function. Okay? So I can say that this is the average of the function plus some correction, which is small, if n is big. Okay? If we notice that, so let's talk about the recursive way of the recursive trapezoidal rule. Why is this the error? Again, what?
Where do we get the expression for the error?
This is the trapezoid. For example, from here, this is the arrow, and now I make it for this plus this plus this. This is the arrow here, and I have a similar one here, the similar one here. So this plus this plus this. Okay. So remember the recursive trapezoidal method. I take Hn to be 1/2 to the n. Therefore, and if you remember, In equals the half of In plus Hn, the sum of x0 plus 2I minus 1 Hn. Yes? You remember this? Okay. So that's my recursive way of evaluation or submitting the integral, and I know what is the error. So again, the error when I use n points is this. Okay? And the error when I use 2 to the n points is this. And if I use 2 to the n plus 1 points, it is this. And what's the difference between e of In plus 1 and e of In? Here I have Hn squared, but here I have Hn plus 1 squared, which is Hn squared over 4. And we have here the averaging of the function using 2 to the n points. And here I have the averaging of the function using 2 to the n plus 1 points. And these are not the same points. And these are not, and the differences between them are not the same. I don't know what are they. But again, if n is too large, this e of In is this c, which is the averaging of the function, plus some correction, which is small. That's what I wanted. And this also is C multiply, because this is C. Okay? So I call this C. So this is also C, but multiplied by Hn squared over 4. And here again, E of In is Chn, C plus small correction, Hn squared. And here, this is this plus small correction. Therefore, if that is small, I can use the two integrals in order to make a more accurate. So how can I build more accurate one? If this is C, if we don't have any error for this C, and this is equal, this is equal. So how can I build something which doesn't have any error? So if I take 4 of this minus 1 of this, the error of that evaluation is 0. Okay. But it's not 0. It is something that is one order lesser than C. Okay. It's of order h squared, and we will see that, but at least you can see the motivation. So we take 4 minus 1 and divide by 3 because I want the integral. Okay. So I have some evaluation, another evaluation of the integral. I take 4 of the second one, 4 of the second one minus 1 of the first one divided by 3. So it is also an evaluation of the integral, but it's better than this and better than this in some way. That's the motivation, and now we will see how we can prove this motivation. Okay. Any question? So at least you have to know this is called the Richardson extrapolation. And that's how we prove it. We use something that we didn't do. Okay. So we will not prove this in the course, but the Euler-Maclaurin summation formula, it is I wrote it here using H. You'll find it in Wikipedia. I think without this H, you will have it f of the integral of f of x from m to n. But you can change it to this way or this form. It is it's important to know that this sum or this infinite sum is an asymptotic expansion. So at every h, there is some point that it is good for us to stop there. Okay, so always it is good. It is for every h we have some point that we should stop there, because the error after that will be larger and larger. Anyway, we see from this summation, this theorem, let's call it, we see that the trapezoidal method has an error of h squared at the first order, and after that of h to the fourth, and then h to the sixth, etc. Okay. So if we use n here to be 2 to the n, we can write this. And if we take n to be 2 to the n plus 1, we can write this. So this is my trapezoidal way using 2 to the n, and this is my evaluation way of the trapezoidal method. When we use 2 to the n plus 1 points. And as you see, these constants doesn't depend on h. Okay? And because they don't depend on h, now I can say that, of course, here I have hn plus 1 to the power of 2k, but hn plus 1 is hn over 2. So it is hn to the 2k divided by 4 to the k. And here you can see that I can cancel the h squared term using 4 of this minus 1 of this. Okay. We have here h squared. Take the first term in this sum. It is hn squared b2 divided by 2 multiplied by this. Okay. Here the h squared term is b2 divided by 2 h squared divided by 4. And then I have another terms of h to the 4th and h to the 6th, and also here. But if I take 4 of this minus 1 of this, I cancel the h squared term, Okay. So that was my motivation, but now we see it in the problem. So 4 of in plus 1 minus in over 3, I will get this using these two equations. And I can write this, and at k equals 1, what is this? When k equals 1, this is 0. So that's my error starts with h to the 4. So my motivation was right. Okay. So that's in plus. So if I calculated I0, I1, I2, I3 in my recursive method, now I can calculate something called I tilde 1, I tilde 2, I tilde 3, I tilde 4. These will be with error of order h squared. These will be of error h to the 4th. Okay, and of course this is better than this, and this is better than this, and this is better than this, and this is better than this, this is better than this, this is okay. Now I have this thing with error of h to the 4th, and also this with error to the h to the 4th. And again, the constants doesn't depend on h. So I can make again something here in order to get I to 2 tildes. Okay. So let's take a break now, and after that we continue. Okay, so now because I can do this iterative way of updating the value, I will call the recursive method 0. Okay. And then the one that was with tilde, I call it now 1. And I can use these two in order to get a better evaluation. Now, let's think. How can I get a better evaluation using, for example, I tilde n plus 1 and I tilde n? Okay. So what we said before is this. Because I have here h to the 2k and h to the 2k, the hn plus 1 is hn over 2. Then I have here h to the 2k divided by 4 to the k. And therefore, I can take, for the first term in this sum, I can take 4 multiplied by this minus this divided by 3, because I want the integral itself. This will be my new evaluation. Now, if I have I tilde n plus 1, and I have I tilde n, how can I use both of them in order to get a better one? So the I tilde n and the I tilde n plus 1, what's the difference between them? The difference is only by this. Okay? So the first term in I tilde n is hn minus 1 to the 2k plus to the 4. Take k plus 1, take k equals 1. So it is h to the 4. And the first term at I tilde n plus 1 is h to the 4th, but divided by what? 16. So what should I take? I should take 16 of this minus I tilde n divided by 15. Okay. So I n 1 was 4 I n 0 minus I n minus 1 0 divided by 3. And now I n 2 is 4 I n 16. I n 1 minus I n minus 1 1 divided by 50. And then the h to the 4th term will cancel. And I will get an error which is of order h to the 6th. Okay. So now we can build a triangle. Remember, hn is b minus a over 2 to the n. I can build the first evaluation is using the trapezoidal rule with n equals 0. So n equals 2 to the n. And when n equals 0, the trapezoidal rule uses only a and b. So it is b minus a over 2, f of a plus f of b. And then the recursive way of the trapezoidal rule is this. So I calculate at first this, and then I calculate this recursively. And then I calculate each column recursively using the previous column. And each element here, I calculate it using the 2 elements. Okay? So that's what I expect to see. Any question? So again, this has an error of order h squared, h to the fourth, h to the sixth, h to the eighth, h to the fifth. So if I use hn, which is 2 to the n segments, or 2 to the n plus 1 points, okay, I can get an error of order what? You can see. So this is 4, this is 10. So it is h to the 2k plus 2n plus 2. So I call this column the k equals 0 column, and then I call it the k equals 1 column. Questions? Okay. So let's see how we can find the integral of this. So now we want to calculate the natural logarithm of 2. So again, when we have when you saw before irrational numbers, how did we calculate it? So for example, ln we can talk about ln 1 plus x and expand the Taylor series. Yeah. But if x is 1 or 2 or 3, it is not so easy to use that Taylor series. And if I want to calculate ln of 2 up to any order that I want, I can write it as an integral and then find an approximation of that integral that I know what's the error. And I know that the error will decrease like h to the 2k or 2n plus 2. Okay? So that's how I define my trapezoidal integration. I define the trapezoidal integration without using the recursive way. I only defined I 3, 0, I 2, 0, I 0, 0. So we know that the integral is the half of f of a plus f of b plus h, the sum of the values of f at xi, where xi equals the x0 plus ih. So that's how I define the trapezoidal integration. And n is the number of segments here. So you can call it capital N here, maybe better. Capital N and capital N go to be consistent. And when we use the Richardson extrapolation k times, so we use it here one time and another time and another time. I define it recursively. So I define the first column to be the trapezoidal integration, and then any other column I find it with the previous value. Okay. So when we write this in this way, we can say also that this is in plus 1, in1 plus in1 minus in minus 1 over it. Okay, so that's how I wrote it here. And here's my example. And also I will the function which is the which gives me the triangle itself. Here, and here is my triangle. Okay. We're finishing now.
Yeah, I don't know.
Okay. So these are my evaluations, and the best evaluation, you think what? What is the best evaluation among these? What do you think? The last one. But if I want to compare, for example, this and this, or this and this, it's not, I'm not quite sure that it's better. I know that this is better than this, than this, than this, than this. And I know that this is better than this, than this. So here we see in bold, you see the numbers that are true. Okay? So these are the numbers that I got here. I write it this. And in bold, you see the numbers that are true. And the real number, or the more exact one up to this digit, up to the 15th digit is this. And here are my errors. Okay. So you can see that the error goes somehow. So you have to see what is h always. So when h here is 1/16, the error goes at the last row. It is 1/16 and 1/16 and 1/16. Okay. And again, with the same way, I can calculate the pi. So how can we calculate the pi? And that's how we can calculate it. We can use, for example, we can use many things. You know, pi, you can represent it in many ways, and one way is to represent it as integral for something that I can calculate, which is which is a polynomial divided by another polynomial. It's 4 divided by 1 plus x squared. And then I use a numerical integration at any precision that I want. Okay. So again, we didn't have to take that break. Your exercise will be uploaded tomorrow. Today. That's it for today. I hope that was clear. Thank you. Thank you.